Consider the physical properties of solid red granite. Even today, in the 21st century, armed with diamond-tipped industrial blades spinning at 10,000 revolutions per minute, the stone violently resists. It degrades modern tooling. It demands constant, massive water cooling just to prevent industrial steel from melting. Red granite is an unforgiving matrix of quartz and feldspar. It is one of the hardest natural materials on this planet. Now direct your attention to the Alexander Column in St. Petersburg. 600 metric tons of solid red granite, a flawless, perfectly symmetrical cylinder rising 25 meters into the air. Not stacked blocks, not a composite structure. A single, continuous, seamless monolith. The official historical ledger dictates a very comforting, almost romantic narrative. It claims that in the 1830s, unskilled peasant laborers using rudimentary iron chisels and wooden mallets hacked this perfect mathematical geometry out of a frozen cliff face. And then they polished it, by hand, using nothing but wet sand, rags, and sheer willpower. We are not historians, we are auditors. And when we audit the sheer mechanical torque, the friction coefficients, the point load dynamics, and the metallurgical tooling required to extract and shape a 600-ton granite monolith, the official narrative completely collapses. How did they survive the math? They didn't chisel them, they machined them. Welcome to Titan Metrics. Let's open the ledger.
Every construction audit must begin at the point of origin, the quarry. Official records state the Alexander Column, along with the 48 massive columns of St. Isaac's Cathedral, were extracted from the Lathe quarry in Finland. How do you extract a flawless 600-ton contiguous block of granite from a solid cliff face in 1830? You cannot use black powder explosives. Explosives send unpredictable shock waves through the crystalline structure of the stone, creating microfractures. If a 600-ton monolith has a single microscopic internal fracture, it will snap under its own weight during transportation. The historical account claims the workers used the plug and feather method. This requires drilling a perfectly straight line of hundreds of deep holes into the solid granite bed, inserting iron wedges and hammering them sequentially until the rock shears off. Let us audit the time and the metallurgy of that claim. To hand drill a single hole 1 inch deep into Mohs 7 quartz granite using a 19th century iron drill bit requires hundreds of heavy hammer strikes. Because the iron is softer than the granite, the drill bit blunts almost instantly. It must be pulled out, sent to a blacksmith forge, heated, reshaped, tempered, and brought back. Now multiply that process. To shear a block 25 meters long and 4 meters thick, you must drill hundreds of holes, several feet deep, perfectly aligned. The ledger requires us to believe that men standing in the freezing mud of Finland hand-drilled thousands of feet into solid granite using iron sticks that deformed every few minutes. Where is the logistical infrastructure for this? How do you maintain the thousands of replacement drill bits required for continuous operation? Where are the thermal records of the blacksmith forges? They are completely absent from the economic records of the quarry.
Let us assume they magically extracted the rough block without fracturing it. Now, it must be shaped into a perfect cylinder. To mathematically shape a material, your cutting tool must be physically harder than the material itself. This is not a theory, it is an unbreakable law of physics. Red granite consists of roughly 30% quartz. On the Mohs scale of mineral hardness, quartz sits at a solid 7. Now, let us audit the tooling available to Auguste de Montferrand's workers in 1830. The Bessemer process, which allowed for the mass production of durable steel, was not invented until 1856. The workers were equipped with wrought iron and low-carbon steel chisels. the maximum hardness of early 19th century iron, roughly 4.5. Observe the mathematical deficit. How do you carve a Mohs 7 quartz matrix with a Mohs 4 iron chisel? It is the physical equivalent of attempting to carve a hardwood table using a stick of frozen butter. The tool degrades faster than the stone. The official records claim thousands of chisels were constantly sent to the blacksmith to be resharpened. But resharpening a soft metal does not alter its molecular density. How do you achieve microscopic, smooth geometric perfection by blunt force percussion? Hitting a crystalline rock with soft metal creates structural stress and uneven divots. It does not create a mathematically perfect cylinder.
And yet, we have the Alexander column. We have the 48 lower columns of St. Isaac's Cathedral, each weighing 114 tons. Every single one of them is geometrically flawless. How do you achieve a perfect cylinder without hammering? You spin it. In mechanical engineering, a perfect radius can only be achieved by establishing a fixed axis of rotation. The massive stone must spin constantly and evenly, while a hardened cutting tool is applied to its surface. This industrial process is called lathe machining. But these monoliths present a secondary, highly complex mathematical challenge. They are not straight pipes. They feature entasis. Entasis is a deliberate, mathematically precise curvature that swells slightly toward the base to correct optical illusions from the ground. How do you cut an entasis curve into a spinning object? The cutting tool cannot be fixed in one static place. It must travel along a secondary calculated path, constantly adjusting its depth of cut by fractions of a millimeter as the hundreds of tons of stone spin. Today, we execute this using CNC industrial lathes, machines the size of buildings, driven by massive electric motors, utilizing tungsten carbide inserts. Are we truly expected to believe that 19th century peasants achieved CNC-level geometric entasis on a 600-ton block by dragging rags covered in wet sand back and forth for months?
If they utilized a lathe, as the geometry explicitly demands, we must audit the torque. To rotate a 600-ton granite cylinder, you must first suspend it. It must rest on journals or bearings at both ends. Let us apply a highly generous variable and assume the engineers used lubricated bronze on oak bearings. 600 metric tons equates to roughly 6 million newtons of force pushing straight down on those bearings. To overcome the static friction, just to get the monolith to move a single millimeter requires roughly 600,000 Newton meters of torque. How much mechanical power is that? To spin this monolith at a sluggish, barely functional 10 revolutions per minute, you would require over 600 kilowatts of continuous, uninterrupted power. That is roughly 840 real horsepower. You would require nearly 1,000 actual living horses chained to a massive gear system, walking in a perfect circle at the exact same speed without stopping. If the speed fluctuates, the cutting tool digs in, shatters, and ruins the stone. But here is the fatal metric in the mechanical ledger. How do you build a gear system or a lathe frame out of timber that can withstand 600,000 Newton meters of torque? You cannot. The wood would instantly compress, splinter, and explode under the sheer point load of the granite. You require a massive frame constructed of forged industrial steel in 1832.
Let us assume the cylinder is miraculously carved. Now it must be moved. The official historical drawings depict the 600-ton Alexander column being rolled over the finished terrain on wooden logs pulled by hemp ropes. Let us audit the ground pressure.
Solid oak has a perpendicular crushing strength of roughly 800 pounds per square inch. When you place a perfectly rigid 600-ton granite cylinder on top of cylindrical wooden logs, the surface area of actual contact is microscopic. It is a tangent line. This concentrates the entire 6 million newtons of force onto a surface area of a few square inches. The mathematical result is a localized pressure exceeding tens of thousands of pounds per square inch. Have you ever placed a 10-ton weight on a wooden pencil? What happens? The oak logs do not roll. They are instantly pulverized into splinters and compressed wood pulp. Furthermore, the soft earth beneath the logs cannot support that point load. The logs would be driven straight down into the dirt like nails, permanently grounding the monolith. To transport an object of this mass over land, you require a stabilized, steel-reinforced rail system spread over a massive surface area to distribute the load. Wooden rollers and hemp ropes are the logistics of a fairy tale. They violate the fundamental equations of load distribution and material failure limits.
Once erected, the monolith displays another impossible metric: the finish. The Alexander column is not just smooth, it exhibits specular reflection. It is polished to a mirror finish. In the science of optics and abrasives, to polish a material to a mirror finish, you must use an abrasive grit that is physically harder than the material itself. Today, we achieve this on granite using silicon carbide or industrial diamond dust. The official narrative claims the 19th century laborers polished it using wet sand and pumice. Let us audit the chemistry. Sand is primarily composed of silica, which is quartz. Pumice is volcanic glass with a hardness of around 6. Granite is also quartz. How do you polish a Mohs 7 stone to a mirror finish using a Mohs 7 abrasive? You cannot. Rubbing quartz against quartz does not polish, it scratches. It creates a dull, frosted surface. You cannot achieve specular, mirror-like reflection without a harder abrasive compound that cuts the microscopic peaks of the stone down to a uniform plateau. Even if they possessed a mysterious, undocumented supply of diamond dust, manual hand polishing inherently applies uneven pressure. A human hand cannot maintain exact, mathematically uniform pressure over a 25-meter cylinder. Uneven pressure creates microscopic waves and divots in the surface, which causes the light reflection to warp and wobble. Look closely at high-resolution photographs of the columns in St. Petersburg. Do you see any warped reflections? Do you see any wobbling in the light? No, you see flawless optical perfection. That level of optical perfection requires a mechanized, pressure-regulated industrial polishing rig. Dragging wet rags over stone does not yield optical perfection.
The architect, Auguste de Montferrand, left behind meticulous, beautifully illustrated albums documenting the construction process. He drafted the wooden scaffolding. He drafted the specialized barges used to float the column down the river. He documented exactly how they allegedly hoisted it into a vertical position using a forest of timber and thousands of men turning capstans. But look at the ledger. Look closely at what is completely missing. Where is the technical blueprint of the machine used to actually cut, turn, and polish the cylinder? Where are the schematics for a 600-ton capacity industrial lathe? Where are the diagrams of the hardened steel cutting mechanisms required to carve the entasis curve? Why would Montferrand document the ropes and the wooden boats in obsessive, colorful detail, but completely omit the single greatest feat of mechanical engineering of the entire 19th century? In the discipline of forensic auditing, the absence of evidence in a heavily documented environment is not an oversight. It is proof of a deficit. You do not hide the blueprints of the machine that built your empire. You hide the fact that you never possessed the machine to begin with.
If the metallurgy of the era was physically incapable of cutting quartz without degrading, if the mechanical torque required to spin the stone vastly exceeded the structural limits of 19th century timber, if the ground pressure annihilated the transport logistics, and if the blueprints of the manufacturing equipment simply do not exist, what exactly are we looking at? The final equation leaves us with only one mathematically viable conclusion. They didn't quarry this rock. They didn't chisel the perfect geometry, and they certainly didn't polish it with wet sand. The monoliths of St. Petersburg, just like the impossible massive blocks of Fort Jefferson and the offshore lighthouses, are the remnants of an inherited infrastructure. The Romanovs and their architects executed an incredible logistical operation in salvaging, transporting, and standing these columns up. That was their true historical achievement. But they were erecting the salvaged parts of an older, vastly superior machine. The timeline is broken. The ledger has been forged. The metallurgical audit is closed, but the logistical anomalies of the old world are everywhere, hiding in plain sight. If you believe a 600-ton cylinder is a mathematical impossibility, wait until you audit the brickwork. If you want to see how the official historical ledger completely fails basic supply chain mathematics, open the next file on your screen. The audit continues.